Okay, we're going to look at section 3.2. And I'm going to talk about how to do these several different ways. Um, all the problems. And these, the easiest way to figure out what the equation for 1 is to think about the transformational form of the graph. See, this parabola got moved over 2, so that makes it x minus 2 to move it plus 2. It got moved down 3, so that would be negative 3 there. And there has to be something that's times it. Well, the a's got to be positive because it's still going up. And on a normal parabola, if you move 1 off the vertex, it goes up 1. Then you move 2 off of it, it goes up 4, which is what this looks like it's doing. 1 over, up 1, over 2, up 4. So it looks like this is just a 1. That's the easiest way to do this one. And I see I asked you to do 2. So if I use transformational form on this, I get y equals, see, it's moved, excuse me, minus 1. So it must be x plus 1. It's moved up 2, so it's got to be plus 2. And it's over 1, up 1, over 2, up 4, so a must be 1. This one was just moved sideways and down. This one's sideways and up. Now 4, if you look at it, if you go over 1, it's down 3. And 2, it's down like maybe 9. Like 3 times 1 and negative. So it's y equal negative 3 times, let's see, how much sideways was this moved? Well, it's moved minus 1, so it must be x plus 1. And if we do the vertical stretch first, reflect it over and stretch it down at here, then it would be here, and it looks like it got moved up 2. So using our transformations, this is what that equation would look like. Okay? Now, let's do 6 here just in case you need more help. So this one, if I move over 1, it looks like a half down. If I move over 2 from the vertex, it's down 2 instead of down 4 like we would expect. So it looks like it's a negative because it's upside down, and it's only half as far down as normal. But it is moved minus 2, so I think it's x plus 2 squared, and the vertex is moved up 3. That's kind of the idea. All right. Now, if it's in general form like these, let's see, which ones you had to do here? 8. And unfortunately, I signed 8 and they mixed up the variables. So let's just call x instead of p's. These should have been p's or this should have been x. Okay. Vertex. Well, you could take Desmos out and graph it and click on it and you get the vertex coordinates. It's going to be a point over some and up some or whatever. You could factor this, I think. Let's see, if you factor out a 3, you get 3 times x squared plus 2x minus 3. And that factors to 3 times x. See, to make a minus 3, we'd have to have a 3 and a 1. And we want a plus 2, so we probably want plus 3x and minus 1x. So it says the x-intercept is at minus 3. Oh, x-intercept. at minus 3 makes the y be 0, and 1 makes the y be 0. So the vertex has to be halfway between minus 3 and 1, halfway between minus 3, 0, and 1, 0 is at minus 1. You could have also gotten that from part of the quadratic formula, which is minus b over 2a takes you to the center line, and then you go either way to find the x-intercepts. But the opposite of b would be negative 6 divided by 2a times 3 times 2 is 6. That turns out to be minus 1. That's the axis of symmetry. That's the coordinate of the vertex. The x-coordinate is minus 1. To find the y-coordinate, I put minus 1 in here. Minus 1 squared is 1 times 3, 3. Minus 1 times 6 is minus 6. Minus 9, so that's minus 15 plus 3, minus 12. There's the vertex. The vertex is always at minus b over 2a, and plug into the function. Minus b over 2a, whatever that number is, put it back in for the x's and find the y value. So you can do it this way. You can factor it and get the center line. If it was in one of these forms, you would just say, oh, it's at 2 minus 3, or at minus 1, 2. Okay? And x, the y-intercept, in general form, that's a y-intercept. That's a y-intercept. If you're putting zeros in for the x's, you only get left with 12 or 4 or minus 1, or in this case, minus 9. 0 for x, you get minus 9. So there's the vertical intercept. Horizontal intercept, you finish the quadratic formula, or in this case, since it factors, there's one at negative 3, 0 and one at 1, 0. So you can factor. You can use the quadratic formula. You could type the equation in Desmos and tap on the x-intercepts. Bunch of ways to do it. Okay? 12. Let's see. I skipped over a few there. Let's go to 19. And I showed how to do 19 several ways in class. If it goes through minus 3, 0, and 1, 0, kind of like this last problem did, then the center line's halfway between at minus 1. So we could say it looks like y equal a times x plus 1 to move it minus 1 squared, plus it's moved up or down something. And then I could put in 0 for x, and I got to get 2 if I plug this in. So if I plug in 0 for x, I get 0 plus 1 squared is 1 times a, so I get 1a plus b has to come out to be 2 for the y. And let's put 1 in for x. 1 plus 1 is 2. Squared is 4a, so I get 4a plus b equals 0, because y would be 0. And if I subtract these two, like take this one from this one, the b's are going to cancel out, and I get 1a from 4a is 3a, and 2 from 0 is negative 2, and a has to be divided by 3, negative 2/3. So I know that's negative 2/3, and then I can go back and if I put negative 2/3 in here, I can figure out what b has to be. Let's see, if it's negative 2/3 for a plus b equals 2, I add 2/3 to both sides, and b is 2 and 2/3. thirds or 6, 7, 8 thirds. That's this form. But it's probably easier to do, see, if that's an x-intercept, that means a factor was x plus 3. If that's an x-intercept, that means a factor was x minus 1. And there would have to be a number in front to stretch or compress it. Can't have plus things out here because then it wouldn't go through these two places. And that's what y would have to be. So if I put in 0 for my x's, I get a to be 0 here. I get a times 3 times negative 1 has to come out to be 0. Putting 0 in, comes out to be 2. If I put in 0 for the x's, I get 2. So negative 1 times 3 is negative 3. So I'll divide by negative 3, and I get a is equal to negative 2 thirds. Same thing we had here. But if I want to get the rest of the equation, I could multiply these out. X times x is x squared. X times minus 1 is minus x. 3 times x is plus 3x. Minus 1x plus 3x is plus 2x. And 3 times minus 1 is minus 3. And that's all times negative 2 thirds. And so in general form, the equation would be minus 2 thirds x squared minus 4 thirds x, because minus 2 thirds times 2 is minus 4 thirds. And then minus 2 thirds times a minus 3 is plus 2. That has a y-intercept of 2, which is what it's supposed to. If I complete the square on this, I could get it to look like this form. So there's lots of ways to go for it. If you're given the x-intercept, I think using the factors is the easiest, and use the y-intercept to figure out the a. And I would do that on all of these. If I'm given the vertex, then I automatically know the transformation. It was moved plus 4 and not up or down, and it has a y-intercept of negative 4. So that, in this case, I would use the transformation form. I would say y equals a times, see, it's moved plus 4, so it's x minus 4 squared and up 0. So I can forget this. I can put in 0 for x, and I'm supposed to get negative 4 and figure out what a is. Let's do that, finish this up. So if I put in 0 for x, I get negative 4 squared, which is 16 times a, is supposed to come out to be negative 4. Divide by 16, and I get a is negative 1/4. So the equation would be negative 1/4 x minus 4 squared. And it was plus 0 because the vertex was moved not up or down. This would be plus 6 on the end, x minus 5, and I'd put this in to figure out the a. This would be x plus 3 squared plus 2 on the outside, and an a times that quantity squared, and I'd use this to figure out what that is, what the a is. Those are the ideas. That's the ideas on those, okay? Now let's go to these. These tend to be the harder ones for students. So let's talk a little bit about this one. I think 32 was the first one in this area. So, a box. So we know what a box looks like. I'm writing kind of light, so it's kind of hard to see it with this green pen. I apologize. There, was that better? A box with a square base. So if the base is square, that means this side and this side are the same length. It's made from a square. And it's supposed to be a square with no curved sides. Made from a square, so each side is equal. Got to remember what these words mean. By cutting 4-inch squares, so I'm cutting a square, so all these sides are 4 inches. I'm doing that out of each corner. And if you do that, then you can fold here and here and here and here and make a box similar to what we did in class. But in class, we didn't know how big to cut these out as or how much we were folding up. Here, they're saying fold up 4 and make the box have a volume of 2,700 cubic inches. Well, the volume of the box is length times width times height. But since this is a square and we're cutting 4 out of each end, this and that and that and that are all the same. So the length and the width are the same. But they want to know how big is the cardboard. So they want to know how big these two numbers are. But since it's a square, they're the same. So if that's what they want us to know, let's call that x. So this length is x minus 4 and minus 4. So the length is x minus 8. X minus 4 and minus 4. X minus 8 is this. And since these are both the same, the width is also x minus 8. And the height is how much we fold up, which is 4 inches. So there's the volume, and that's a parabola. And we want to maximize it. Well, let's see here. This we want to, the box holds, oh no, we don't want to maximize it. We want to make the volume equal to 2,700 cubic inches. So we want 2,700 to equal x minus 8 squared times 4. So you could multiply this out, take it times 4, subtract 100, make it 0 equals something that looks like ax squared plus bx plus c, and use the quadratic formula. Multiply all this out, subtract the 200 so it's equal to 0, then you can use the quadratic formula. But since x is only in one spot, we should be able to undo this. Divide by 4. So 2,700 divided by 4 is 675 equals x minus 8 squared. So then we take the square root of both sides to get rid of the square. And that's always plus or minus. Square root of something squared is just that. And then add 8. So the size of the paper is either 8 plus this or 8 minus this. Well, 8 squared is 64. This is way bigger, so 8 minus this would be negative. And we don't want a negative size paper, so the size of cardboard, the cardboard side must be 8 plus the square root of 675. And we're doing this in inches, so this inches is the length and the width of the cardboard. Okay. A farmer wishes to enclose 2 pens. And he has 500 feet of fencing. It's got 500 feet to make the fence, the fence, the fence, the fence, the fence, the fence, and the fence. And it wants to know the dimensions that give a maximum area. Dimensions are how wide is it or how long is it? And we don't know that these are squares, so we better call this something different, but they certainly look like rectangles. They should have said that these are rectangles, so we're not assuming. If you can use X amount of fencing here, X amount of fencing there, and X amount there, and you got to use Y to get across there, and if these are the same size, it would be Y here and Y there, then the 500 feet of fencing would have to do all 3 X's and all 4 Y's. Now it is possible to call the whole thing Y, and it just changed the area equation just a little bit. This won't tell us the area or how to maximize the area. It's just a constraint. We are limited to 500 feet of fencing to cover these. It constrains the maximum sizes of things. It's called a constraint. What we want to maximize is the area, which on a rectangle is width times length, or length times width, whatever. It's going to be X times Y if you're just doing one pen. And if you maximize one and the other one's the same size, you would have the dimensions for both. Or you could maximize the big pen, and we could have called this X times Y for the whole thing. But the way I did it, the area of the whole thing is X times 2Y. Now, this is what I want to maximize, but it's got too many variables. I'm going to use the constraint to get rid of either the X or the Y. And I'm going to choose to get rid of the Y. So I'm going to solve for Y here by subtracting 3X for both sides, dividing both sides by 4, and I get Y is equal to 500 divided by 4 is 125, and negative 3x divided by 4 is negative 3/4 x. If I put this in place the y, I have to double it because it's times 2. So I get x times 125 doubled, 250. 3/4 times 2 is negative 3/2. Oh, no. Yeah. Double 3/4, and I get 6/4 or 3/2 x. That's the 2y. That's this doubled. And it's also times x, and that's the area that's now all in terms of x. And this has, if I want to maximize, it's going to be at the center line for x. Now, if I think about this as a factor and a factor, the center line's halfway between these. This crosses the x-axis at 0, and this crosses the x-axis at whatever makes this be 0. This is not the way I taught it in class, but another way to look at it. So 250 minus 3/2 x. I want to know what makes that be 0. So I'll add 3/2 x to both sides. I could have subtracted 250, but I like keeping things positive. And then I can multiply both sides by 2/3. And I get x is equal to 500 divided by 3. And that's the x-intercept. So there's an x-intercept at 500 divided by 3 and 1 at 0. 500 divided by 3 is 166 or something like that. So there's an x-intercept at 0. This is an upside down parabola, and another one out here at 500 thirds. So the maximum's halfway between. So halfway between 0 and 500 thirds is 250 thirds. And that's the x that maximizes this. If I divide 3 in there, I get 83 1/3, I believe, feet. Now, you could have just typed this into your calculator or Desmos and clicked on the vertex, and it would have given you the x value that maximizes it. But that's only one of the dimensions, 83 1/3, 83 1/3, 83 1/3. If I add those up and take them away from 500 and then divide by 4, I'll have the y. If I take 83 1/3 times 3, that'll add up those 3, subtract it from 500 and divide by 4, I'll find the y. Or I can take 4/3 times 83 1/3, 3/4 times 83 1/3, subtract it from 125, and I'll have y. And so y turns out to be 62.5 feet, I believe, if you do that. So we now know the 2 dimensions of the pen. If you wanted to know the maximum area, when you found the vertex, the curve was the area. It happened at this x value. The y value is the area. And it didn't ask for the area. It asked what are the dimensions that maximize the area. And 34 is another one that asks you to do basically the same kind of stuff as 33. So I'll leave that one for you to try to do on your own.